All right, so yeah, this is slightly different. I mean, uh, I was the person that Professor Bhaskaran had mentioned in his talk, and I had started out as a cosmologist, but eventually I got into doing experiments, and to do experiments, I got into instrumentation. So I'll just have to explain the basic approach and how we've been going about this whole thing. And so the idea was that when I was getting into experiments, so the whole idea was that if we got into experiments, we would try to actually, we need instruments. So we actually decided to start from instrumentation itself. And we try to build the instruments, set up the experiments using the instruments that we'd built, and do the computations that were required in order to to bridge the thing all the way out to theory. So we'd have to have all four of these occurring under the same roof. That was the whole plan. And the idea was that we would first build up these instruments and build them up from scratch completely. And to the point that we had an entire lab where every single instrument had been built by us. All right. And eventually, that would allow us to do research and do it on a completely competitive basis with all the other places in the West that I'd been used to. I'd actually done my PhD in particle theory, and I'd gotten into cosmology and various things of that sort. I was used to doing research I mean, my record letters were written by Professor Salam, and in some of my seminars we had Feynman sitting there and so on. So I was used to things at that particular level. So if we had to do it at that level, this was the only way of doing it. All right. And so even though I had no clue of experiments or instrumentation, I decided to go into it. And this is a talk about what happened subsequently. Okay. So we started off with trying to make a scanning tunneling microscope. You open up any of your computers, you'll see something of this sort. You'll have a whole bunch of components which are on the centimeter scale. You magnify that slightly, a part of it. You see tracks, etc., which are on the millimeter scale. And then there is an IC out there which you can open out. And if you open out that IC, you have, once again, circuits, except that all the tracks are now on the micrometer scale. They're all microns wide. Within that, there are ICs that you can open out. On the 100 nanometer scale, you see something of this sort. Magnify that, and you now see this is a strain of gold. You see steps which are essentially atomic in size. And you have this, the rest of it is silicon. This we took from the net. This wasn't something that we resolved, but this we resolved with our own microscope. You go one step further and you start seeing atoms. All right. And the way you actually end up doing this is that you see the whole thing by feel. I mean, so in a scanning tunneling microscope or in a scanning probe microscope, the probe is like your finger, and you're actually, you think of a person who's actually reading Braille, and he's moving his finger over the Braille itself, and through feel he's able to actually read the entire thing. So here you have a finger, all right, and you've got, this is the probe. It's just a piece of platinum iridium wire. You bring it very close to the surface. You apply a bias, and a small quantum tunneling current begins to flow. That's the sensation at the tip of the finger. And it is through that sensation that you're actually able to feel the whole surface and reconstruct it. Using a computer, of course, you use the quantum tunneling currents, and you feed them to an image processing program on the computer, and the computer then reconstructs the entire surface. All right. So we started building it. I had absolutely no clue how to do it, but we got together a team, but we didn't have the confidence that we would get the whole thing working. So we started putting all the electronics, building it in pieces, and this is where the whole scanning was done. We brought a probe very, very close, and when we're talking about bringing it close enough to start the tunneling off, you're talking about bringing it in a controlled way to within 3 or 4 atomic distances of the surface, all right, and applying the bias. And when you bring it that close, you have to make sure that there are no vibrations, because the slightest vibration is going to make this whole thing crash into the surface. So we had to actually try to isolate. We put it on a stool and then the feet of the stool in sand in the hope that if any vibrations come in, then they'll have to travel through the sand, and that's where all the energy would be taken out. But now looking at this, you have to be a true believer to think that anything's going to come out of it, leave alone atoms. But that's exactly what happened. I mean, we managed to, in fact, we'd stepped out late in the evening. That's when we were scanning, and got a phone call saying, hey, I think you should come back, because I think I'm looking at atoms. We rushed back, and this is what the person showed us. This is now amplifying further and further, and now these are variations in the atomic scale, a small amount of image processing, and we were getting atoms. And this one was, at that point, a collaborative effort with IIT Kanpur and IUAC, but all of this was happening in Delhi. All right, but as you can see, all this had been built up completely from scratch. All the electronics, everything had to be designed and worked out. And so this one then later evolved. All the electronics collapsed into a single box. This whole thing went into, this was the vibration isolation stage. You had a small scan head out here. All this came out of a master design thesis, which I guided along with another faculty member, Amit Ray, in IIT Kanpur. And this was now in a form in which this whole thing started becoming competitive with things that MNCs were beginning to produce. And this one, when I say that we built this was not an assembly job. We designed and machined every single mechanical component with our own hands on lathes, milling machines, surface grinders, and so on. We designed and machined and soldered all the electronics and resoldered it and took it through all the generations over these last decade or a decade and a half. It has gone from DIP components to SMDs to BGAs and so on. And we had to design and redesign it to keep up with all the changes in electronics. And then, of course, we wrote every single line of the software. And we also then worked out all the ergonomics and finally made it user-friendly enough for all this to work out. And then so now routinely we're able to, we just make the thing, resolve atoms, make sure that we're getting the whole atomic lattice working. This is, we can, once you have all the information that you've gathered, you can also visualize the entire thing in 3 dimensions. You can rotate it and so on. But the interesting thing here is that the software that we're using as the base is called Mayavi. It was written by a person called Prabhu, who was doing his PhD at IIT Madras, in which he was actually trying to visualize, he was in aeronautical engineering, he was trying to visualize flows, etc. And so Mayavi is the illusionist, is a perfect name for an image processing program, and that was used as the base for what we did. So what you're seeing here is Indian technology from the base upwards. Even the software and the packages that were used for that particular software were also Indian. All right, everything, I mean, is just the ultimate make in India thing. I mean, this is what these people dream of when they're talking about it, but this is what it was. And now these are grains of bismuth telluride that we're looking at, and we zoom in on them with the microscope until you see the atomic lattice. So you start with a whole bunch of grains. This is on the micron scale, and you keep on zooming, and the grains become bigger and bigger until you're left with one grain, and yet you go on zooming until you've resolved the atomic lattice. All right, so this just gives you the sheer power of this whole thing. And I mean, this is going over 4 orders of magnitude. And of course, if you were to zoom further, there'd be new structures. So there's as much of structure as you're going down in scale as when you're going up. I mean, you go up to the solar system, and then, of course, we're at the edge of the Milky Way, and then you go to the local cluster of galaxies, and then so on. I mean, so there are structures as you're going up, but there are also structures as you're going down. And this whole thing about the richness of physics as you span, orders and orders of magnitude in length and time is exactly what keeps us totally mesmerized as physicists. And then, so after this, of course, it was further development. We went on to putting in It was just topography, but there was also local density of states, and then local barrier height, which is the local work function. And we resolve all of these with exactly not only atomic but subatomic resolution. So what we're talking about is we walk over an atom in 25 steps. So the resolution is 1/25th the size of the atom. All right. So the atom is already a big object. And then after that, the next step was to try to make a vacuum STM, so that, but it was still a low vacuum STM right now, because in order to make it ultra high vacuum, you need pumps, which again, I mean, the whole philosophy was that we would not buy anything out. We would design everything from scratch. And so at the moment, we haven't been able to make intermediate pumps like turbomolecular pumps. The vacuum ion pump is something that we have made considerable progress towards. So once we get to 10 to the minus 6, we can take it to 10 to the minus 9. We made the full range vacuum gauge. We can measure pressures from from 1 bar, which is the atmosphere, all the way out to 10 to the minus 9. And possibly, I mean, the thing should work all the way to 10 to the minus 11, but we haven't gotten chambers that we could actually test. So we've gone up only to 10 to the minus 9. But you're not allowed to have vibrations, because the moment you have vibrations, you're not going to be able to resolve the atoms at all. So, so what you do is that you pump with a rotary, and then you connect it to a sorption pump, which has absolutely no vibrations, and you can hold that vacuum for about 5 hours without a problem. And you can stand for 5 hours, and then you'd have to recharge and go through the cycle again. And then we've taken it down to liquid nitrogen temperatures. Liquid nitrogen is easy to work with. It's also very inexpensive and is generally available. And it's the same price as full cream milk. I mean, we've been watching it over the last 6-7 years. As milk has become more and more expensive, it went from 40 rupees now to 55-60. Liquid nitrogen has also gone only up to 60 rupees a liter. So if you really want to do your experiments, just don't drink your milk. Just buy the liquid nitrogen and your experiment will happen, all right, with the same money. We've now moved ahead and made the atomic force microscope using a tuning fork to begin with. And we have resolved a whole bunch of things, which I'll just show you. This is fascinating because what you can do is that you can take one of these tuning forks that you get routinely as a part of electronics, open it out, it'll oscillate in vacuum before you open it out. It oscillates 30,000 times a second. You have to make a jig, which we did do, with which we can attach a tip here, and then we can etch it so we can get a very fine tip. You get it vibrating, and you bring it very close to the surface. And when you bring it very close to the surface, the tip begins to feel the van der Waals forces. And those are attractive, so it tends to stick there. And just that hesitation makes, because it hangs around there for just a little longer, it increases the time period. And then using a lock-in amplifier, which also we designed and made, all right, I mean, according to the same philosophy, all right, we were able to now pick out changes of only 1 part in 10 to the 7. It's a few millihertz in 10,000 hertz that we could pick out. And using that, interestingly, what we did was that we opened out, this is in 8549, we opened it out, and you can see this 1985 ADI, which is Analog Devices Incorporated. It's written on top of it. This is the top layer. This is something we got from their website. Opened out that chip and then scanned it with this, and you use just that shift in frequency in order to image this. And you could see this is the first image that we got with ADI 1985 using the AFM and the whole feedback loop. And we've taken that further. We now can resolve monolayers of MOS2 and so on, various other things. You can, I mean, in 25 minutes, I can't tell you all this. So, but there is, fortunately, the organizers of the conference have kindly have been kind enough to promote this whole thing. So they've given us a stall. You can go there and you can watch many of these movies and things of that sort in much greater detail. After that, so the point to ponder right now is, should we import, let's say, 15 crore STMs and put them in 2 centers where they're accessed only by trained operators, or should we use the money to put literally 100 air, vacuum, and low temperature STMs? The price ratios are such that instead of these 2, we could put 100 of them, completely democratize the research, all right? It goes into all the universities and institutes and so on in the hands of PhD students and just let them loose. I mean, if you've got these 15 crore things, people are scared to touch them. Yeah? They'll just, whereas if this is completely indigenous, we give it out, we train PhD students and we just say, do whatever research you want to, all right? Let's answer this question by seeing what did actually happen, because we have by now installed 70 of these. So we've got, this is a paper that's come out of Puneet at CUSB, which is the Central University of South Bihar. He has now resolved, he was studying these monolayers, and he's resolved all these molecules with the same STM, all right, with the vacuum version of it. But he has actually resolved these, and he's been making molecular switches and so on, all right, with this. This is another thing which has come out of IG CAR, where they're doing 3D topological insulator properties, topography, and spectroscopy. You have this thing coming out of IIT Delhi, Sujit, who's probably here. He has been doing quantum anomalous Hall effect measurements, spectroscopy, and topography again. It is this, we ourselves did this on graphene. We've been resolving all sorts of Moiré lattices and so on. And there are other things that we've resolved that I'll show you. And this has come out of Sikkim University. So, these are just examples of STMs that have been given. And one of the people who was a part of the original team, and in fact, the originator is sitting there, Anjan. And so now this whole idea has gone, the whole thing has spread to 70 places at least within the country, and we've even given one to NTU, all right, which is in Singapore. And people are doing things with it. Yeah, they're writing really good papers. So, if I go back to this question, these are just representative among the 70. I can't, 25 minutes give you all of this. There are other people. Sudipto is here. Sudipto gave a whole talk on this, and he did all sorts of things with the STM that he has. Jinesh at ISRO has written at least 10 papers, many of them on memristors and so on. Avijit at the IIT Bhubaneswar, whole bunch of other people, all right? And so the thing is that if those 15 or 30 crores had gone into these 100 odd STMs, not only would there have been a lot of work getting done, but that money would have gone into building then the UHV and the ultra low temperature STMs, because it would have remained in the country, it would have gone to the people who are trying to develop this further, and in a very short while we would have had a completely indigenous base, right? So should we do that? And so I have to go back to saying, well, the answer, my friend, is blowing in the wind. The answer is blowing in the wind. I don't know how many people in this generation are familiar with the song, Bob Dylan, all right? So then the next thing that we built was this physical quantities measurement system for doing resistance studies. And measuring resistances, we can now measure it. Resistances over 21 orders of magnitude, from 10 to the minus 5 ohms going all the way out to 10 to the 15 ohms, all right, which is a petaohm. And we can do AC magnetic susceptibility measurements and so on. And this is between 80 Kelvin. We're still stuck with liquid nitrogen, all right? We haven't yet gone down to liquid helium, although we are now studying exactly how to do that. We've started understanding some of the designs and so on. But with this, then, we could do We can explore superconductivity. I can't get into the details in the 25 minutes, but semiconductivity, we've done a whole bunch of that, magnetism, and of course phase transitions, critical exponents, and so on. Now, a typical thing is say getting the current voltage characteristics of diodes, and you can see that here, if you take the voltage versus current, it's almost completely insulating, and here it's almost completely conducting. So the resistance changes by about 8 or 10 orders of magnitude in just one run. So you have to build in a certain amount of intelligence in order to figure out how to make this measurement. But this is just done automatically. I mean, you just program it in and it'll just do it. And this is done from 80 to 450 in steps of 25 Kelvin, all right? And you get this whole set of curves out here. Here, of course, you don't get any structure. You need something which is much, much finer. You have to be able to take steps which are 1 millivolt and be able to measure much smaller currents. So between this, we measured that. We can now measure all the way down to 1 picoampere. And now this is not Keithley or anything. This is stuff that we have built again from scratch. All the picoammeters, the source and measurement units have all been built by us, all right? And we can go down to, in fact, noise levels of as low as a few hundred femtoamperes. And this one, of course, can be fit almost perfectly. So the red line and the red dots that you see are experimental data, and the blue line is a fit to the Shockley ideal diode equation, all right? And then, I mean, we've done stuff in magnetism, and then we've now gotten into the thermal properties. So we built a Seebeck coefficient in a thermal conductivity system with which we can get the whole figure of merit out and so on. So anyone who's into thermopower can use this, and this one now is 80 to 800 Kelvin, all right? It goes up to 500 degrees centigrade. And then the next thing, of course, if we had to close this loop, we had to be able to make samples and so on. So we built a high-end CVD system. And one of the things that we did with it initially was to grow graphene. And the way you grow graphene is this. You just pass methane and hydrogen over copper that you heat to about 1,000 degrees, all right? And then when you cool it down, the graphene just forms on top of it, all right? We won't get into how, but it just does, all right? And when it does, and you cool it down, the copper shrinks, and the graphene doesn't shrink as much. So you get these wrinkles on it, and it's with the because of the wrinkles that you actually start seeing the graphene. That's how it becomes a little easier to see. So we just did that with copper here. We annealed it, and then we ran this. There's supposed to be graphene on top of it. Almost impossible to see, but you keep on magnifying it, and now here you start seeing the wrinkles out here. So this shows you that graphene has formed, and here you see the wrinkles even more clearly. But then we have an STM with which we can see it much better. So we looked at it under the STM, we start seeing the wrinkles much better, but we go one step further, and lo and behold, you not only see the wrinkles, but you resolve the atoms. You see the whole hexene, the benzene rings on top of the atoms. These are beautiful images that you see of the wrinkles with the atoms fully resolved on the wrinkles, all right? So this is stuff that we did with our STM. But I've given you now 6, 7 examples of what people were able to do. And so I'm a very strong advocate of the fact that instead of giving 30, 40 crores and sending them abroad, we have to put the money here, democratize the whole thing, make it available to 100 universities, to 500 PhD students to just work with. And in a short while, we'll absorb the whole thing. The whole technology will just come, and it'll just become as Indian. People will even forget that the Germans were the ones who invented this. They'll think that it was the Indians who did it. All right. So after that, the next thing that we did was to move on to making an atomic layer deposition system where the control is one atomic layer at a time. Now, if you grow with a physical vapor deposition, you can grow at the rate of about 100 nanometers to 1 micrometer a minute. With the CVD, the control is a little more. It's 10 to 100 nanometers per minute. And with the ALD, it is 0.1. You do one. So it's a pulse system. You send in pulses of precursors, and with every pulse, you get one layer. So you get, and it's completely, it's conformal, by which I mean that if you have a structure like this will coat it exactly like, the thickness will be uniform right through. In this one, this is what it'll be like for chemical vapor deposition. And if it's physical vapor deposition, it's just line of sight. You'll just get this much coated. These edges won't get coated at all, nor will these get coated. It'll just be here, here, and here. Okay? But with ALD, you get completely conformal coatings. All right, so we built this. We built it for ISRO, and these are some of the. Here we did buy these very fast valves from outside, but everything else was our own thing, and all the electronics, of course, we built. This is the GUI that we have, and these are the coatings that we. So with 250 pulses, this is what you get. This is with 500, and this is with 750. I mean, as the thickness grows, just because of the reflection, the color itself keeps on changing. But the uniformity, you can see just by looking at it, how uniform that whole thing is. The level of uniformity, of course, goes up if we use plasma-enhanced ALDs or plasma-enhanced CVDs. So that's the next thing that is on the agenda. This is now a 2-inch wafer that we coated. All right. And then, wait, what is now? Huh? 5 minutes, yeah. Okay, no, I'm almost done. But except that this has stopped working again. What has happened here? Wait, let's just continue with. For some reason, this is just frozen, yeah? I have no idea. This has to be counted out. Okay, battery is running low. Good God, what has happened here? Oh, okay, this wasn't connected. All right, so this is timeout. All right, okay. All right, wait, do we have to wait for it to charge before it starts operating again? It is working now, okay. All right, so how are we doing all this in India? Well, we're having to consolidate our base here. So we've now had about, as I said, 70 of these. So it's 60 air STMs, 6 vacuum STMs, and then it's 4 low temperature STMs, 40 of these physical quantity measurement systems, 27 fully automated CVDs and so on, 1 ALD, and then there are data acquisition systems, etc. And then we have to widen the whole thing. We've developed joint PhD. So we've run a PhD program from the company. We graduated our first student. So it was with NIT Calicut and BITS Pilani. The degrees are given by those people. But I mean, the research is done at Quasar. And then MOUs on the on the ALD with, and then with IUAC, we've got that. Technology transfers of both the full range vacuum gauge and the vacuum ion pumps are all from BRC. And then this is done during the PhD, all sorts of structures with different morphologies that you could use for enhancing HERs, I mean these hydrogen evolution reactions and so on. And then, of course, some of these papers were written. One of these papers, I mean, I personally didn't have a very high opinion of our own papers, even though I myself I should be the advocate. But one of them made it, to my surprise, to the cover page of this journal, whatever it is, of vacuum science and technology. And then, so eventually the conclusions are that slowly the lab is now becoming reasonably respectable. We've been able to build a whole bunch of scanning probe microscopes, STMs, vacuum low temperature air STMs, the AFM itself. CVDs for solids, liquids, gases. We put in liquid precursor vaporizers and so on, the ALD itself, now the atomic layer deposition system. I'm told that very few people have ALDs, and so almost anything you do with an ALD you can publish. So it means that you can, at least as far as PhD students go, you can get all sorts of things done. 80 to 800 electrical transport, Seebeck, thermal conductivity, AC magnetic susceptibility, vibrating sample magnetometers, Hall coefficient measurement system. So we put this, slowly we're trying to get towards making a fab. And so a PhD student has a PhD program has started, and in condensed matter, material science, and nanotechnology. So at least we've managed to get that far. Okay, thank you.
Thank you so much.
Okay.
So now, yeah, open for questions.
Congratulations, Professor Sadev.
Oh, okay, thank you. I mean, this is still only a fraction of what we want to do. But yeah, it's not a non-zero. It is some small signal.
So great work. So I have a question: how the resolution of your instrument like STM compares with the Bruker or Park Instruments machine?
We can take them on.
Okay, that's very nice.
We, I mean, they have the UHV thing, and they have very low temperature. The point is, the moment you go down to about 10 Kelvin, you also get the magnetic field, because you're in the superconducting regime, and you can now start, you can start getting fields of 10 Tesla, because all you have to do is, there's no resistance, right? So you just need to be able to charge those particular coils, and you get to these very large fields. So those are the two major steps. Point is, the moment we get UHV in this, then we are competitive. We take them on.
Temperature STM is comparable, or
They haven't been able to sell one, yeah. I mean, once we brought in the room temperature ones. So that is out.
Make the tip. What is
Oh, the tip isn't, we'll show it to you, yeah. I mean, you can make a few yourself. I mean, that's the best way of showing you how to do it, is to make you do it.
Yeah, there.
Yeah.
Sir, very, very nice talk, and thank you very much. So basically, I had a small question. So regarding surface, especially for RT STMs, I'm actually not very familiar with them. So how do we clean, for example, bismuth, selenide and telluride? On research level, we have seen sometimes the surface is very contaminated. Do you have some?
No, wait. I mean, we are right now, we don't have any facility for in situ cleaving or anything of that sort, all right? I mean, all this is, we are doing those surfaces that don't easily get oxidized or anything of that sort. So these are all the things that are there are under, are basically things that survive in air itself. You're right, that the moment we do UHV, we also then have to have all the manipulators and everything, and all the feed-throughs, the mechanical feed-throughs that allow us to do things completely inside the vacuum without breaking it. So those steps will have to be taken, and that we have not yet brought under control.
Yeah, so this last question, please. And you can visit.
You can just visit the stall there. You can sit there and ask as many questions as you want.
Yeah. So thank you very much for the very informative talk. So my doubt is for all this thermal conductivity stuff. You had mentioned about the thermal conductivity.
Right. Yeah.
So we were also trying to make the thermal conductivity setup, and one of the major challenges which we are facing is this dissipation, like the heat dissipation,
The
from
heat-
the heat wires and from the material itself. So what are measures we can take for reducing that or looking into that problem?
Well, so far, the results that we've gotten and which we are confident about go up only to about 300 degrees centigrade. From 300 to, and the problem becomes more and more severe as you go higher and higher in temperature. We are using right now, we're not using the pulse thing where you just hit something with a laser pulse and then you heat it up and then you see how it's cooling down. We are using a pulse power, so we're giving pulses, power pulses, we're heating it up and then letting it cool down. Now with that, you have to have you have to take certain measures in which you have reference samples where you know what the thermal conductivity is and so on, and you should be able to compare with that. But up to 300, we're being able to match the data of reference samples. Beyond that, we are right now, it's work in progress. So, once we get it working, we can answer that, in a more convincing way.